The content of my talk is listed here. Introduction. A Space Solar Power System, SSPS, is composed of a space segment and a ground segment. The launching cost is an important factor and could be reduced to 1/100th due to the development of reusable rocket vehicles and commercial uses of space, especially space tourism. So SSPS could be competitive with conventional ways of electric power generation, such as oil-fired or nuclear power stations. However, the air pollution caused by many launches may cause a problem. To solve this issue, new rocket engines are being studied eagerly. In Japan, only a few research issues for SSPS are being studied. This paper selects and presents the following basic research issues. 1. Space structure for foreign antenna parts, carried out by JAXA. Beamforming technology by Kyoto University. Basic research for large antennas by Nihon University. Microwave propelled rocket by the University of Tokyo. The first topic is a construction method of a large planar antenna. A large space system must be divided into smaller parts, and they should be launched separately and deployed in orbit. So a novel automated construction method is proposed. The final objective is to construct a 30-meter class large planar antenna from a single launch payload. The manufactured model is composed of 2 rows of 4 panels each, as shown in figure 1 here. Actually, this figure shows the deployment procedure. At first, the first row is deployed. A guide rail is formed with the C channels on one side of the deployed panels. Next, the second row tip and the slider are connected by using the solenoid connection mechanism SCM. Then the slider is towed with a panel deployment mechanism PDM mounted on the top tip of the first row. Now the second row is deployed along the guide rail. They carried out experiment verification. In the ground deployment experiment, 4 helium balloons are attached to each row for gravity compensation, shown in this figure. Left side shows the before deployment and this side after deployment. Figure 2 shows the scene of experiment. The first row is deployed in advance, and the second row starts extension. The balloons move according to its extension. We confirmed that at the start of the deployment of the second row, the SCM operation can connect the second row tip to the guide rail of the first row. However, the success rate of the connection was about 80%. It is due to insufficient margin for the SCM's force, and so on. And also we confirmed that it's possible to deploy the second row panels with a PDM operation. Next topic is a beamforming technology. In microwave power transmission between fixed points, a well-confined microwave beam must be designed. The electromagnetic field can be expanded using spherical Bessel functions, Legendre functions, and exponential functions. The mode of a spherical wave is determined by the order L and M. The main parameters of a beam are the beam divergence angle theta and the diameter of the beam waist d sub w. They are dependent on the maximum order of L. as shown in this equation. The field of a synthesized spherical wave in a beam shape was studied as shown in figure 3. The Lmax is set as 377 and the frequency is 5.8 GHz. The white solid lines show the beam divergence angle theta, in this case 0.48 degree. The white dotted lines show 2 theta, which correspond to the first null angle. So you can see there are many side lobes. Next, assuming a 25 meter square antennas, the electric field of the wave at the position of each antenna element was calculated. The field radiated by the phased array antenna with the same excitation was calculated. The result shows the power density profile was similar to that of the original spherical wave. Then application to both sides retrodirective system. A retrodirective system is a beam control technique for accurate microwave power transmission. A part of the received signal is taken out by the directional coupler and re-radiated as a pilot signal through the phase conjugate circuit. We newly propose to apply the retrodirective system to both transmitting and receiving antennas in the beam-forming system. As shown in figure 4, the transmitting antenna is left side and the receiving antenna is right side. The antenna size was 50 meters in diameter. The propagation distance of the beam was 10 kilometers. The frequencies of both the pilot signal and the power signal were 5.58 GHz in orthogonal polarizations. The size of the analysis space and so on were assumed like this. The calculated result is summarized according to the iteration number n. In figure A, n equals 1, a large amount of energy leaked in the side lobes. In figure B, the leaked energy was suppressed. In figure C, n equals 299, the ideal beam shape was obtained. The beam correction efficiency reached 99.99%. Next, basic research for large antennas. As you may know, NASA's reference system uses 200 million dipoles. Each dipole is half wavelength in length and a quarter wavelength in height. It may be impossible to fabricate this kind of antenna. To realize simplification and mass production for large antennas, we carried out the following research topics. As radiating elements of an array antenna, we proposed ultra-low profile dipole. As feeding circuits of microwave to radiating elements, partial drive, and uniform excitation techniques. As folding mechanical structures, we proposed a multiple two-dimensional deployment. In this presentation, the partial drive technique is presented. Partial drive technique is depicted in figure 5. Here, in the left side, we have the driven element and the parasitic element. The direct wave from a driven element illuminates a parasite. Then the parasite radiates to space. The two waves can be summed in space. As a result, the antenna acts as two elements through though the parasite is not fed. The right side shows a more realistic antenna including a reflector. In this case, the reflected wave and the direct wave should be considered. Analysis was carried out for the illustration below. The radiating element is a half-wavelength dipole, one driven element, and two parasitic elements on both sides. The radiation pattern was computed changing element height h and the separation d. The optimized configuration was h equal 0.63 lambda and d equal 0.60 lambda. The radiation patterns are shown in this figure by the dotted lines. The first nodes are clear, and the first lobe level is low in E-plane and H-plane. We carried out experiment using the setup as shown in figure. Here is a driven element, and these are parasite. Driven element is supported by coaxial cable, and the parasite are supported by formed plastic. The measured pattern are illustrated by the solid line in figure 6. The patterns agree well with the computed ones in the E and H planes. The antenna gain is 12.8 dBi. The antenna gain of the equivalent 3-element array is 12.9 dBi. The driven element can be reduced from 3 to 1 without gain penalty. Next, microwave propelled rocket. A microwave propelled rocket gets its energy via microwave beam from the ground. It has three features. First, a high payload ratio can be achieved because the vehicle need not carry fuel and oxidizer on board. A millimeter wave generator is reusable for multiple launches. High pressure gas for thrusting is produced so that no turbopump system is required. For these reasons, a micro rocket is expected to achieve drastic launch cost reduction, and it's of non-toxicity, non-explosive, and no air pollution. As shown in figure 8, a micro rocket comprises a cylindrical tube and a closed end called a thrust wall. Reed valves are installed on the tube wall here. The engine cycle is present also in this figure. At the first stage, a millimeter wave beam is line focused by a concentrator, and atmospheric breakdown occurs near the thrust wall. Millimeter wave supported detonation wave propagates towards the thruster exit. At the time when the MSD wave is exhausted through the tube exit, the instant millimeter wave pulse is suspended. An expansion wave propagates upstream from the exit to the thrust wall. When the expansion wave reaches the thrust wall, it's reflected, generating negative pressure. Then the reed valve opens and fresh air is taken in. As for experiment, in 2003, a miniature rocket model weighing 10 grams was lifted to 2-meter altitude. In 2009, a thruster model with 126 grams was launched to 1.2-meter altitude, as shown in this figure. Simulation of the propagation of ionization front. Atmospheric millimeter wave discharges are known to exhibit a unique filamentary plasma structure. This figure portrays the computed plasma density in the left figure and the luminescence distribution in the right figure. In both results, plasmoid pitch was approximately 0.9 lambda. Then we estimate the cost. We propose to replace the first stage of H2B rocket by microwave rocket. We estimate launch cost based on rocket manufacturing, ground construction, and operation costs. The microwave rocket weight, the payload mass, and the fairing mass are assumed like this. The first stage microwave rocket's cutoff velocity is also assumed. The microwave rocket manufacturing cost is $3 million. The second stage is $25 million. Accordingly, the total manufacturing cost is $28 million per launch. In comparison, an H2B rocket costs $110 million per launch. As for the energy supply through millimeter wave beam, the frequency is 110 gigahertz. The minimum beam power to reach the cutoff velocity was shown 188 gigawatt at the beam spot size 4.25 meter. It is estimated that the construction cost is $33.50 million and electricity expense is $179 kilo. Accordingly, the launch cost per unit payload was estimated using the following equation. The result is shown in Figure 11. The abscissa is a launch count. At 42 launches, the cost becomes lower than that of the conventional H2B over this line. At 2,000 launches, the construction cost of the beam facility is fully amortized. The cost reduction reaches 77%. Thank you for your attendance to my presentation from various sides of the world.